Hello and welcome to today's session. In today's session, I am going to make you familiar with deep learning. Deep learning is a subset of machine learning that focuses on using neural networks with many layers, hence deep, to model complex patterns in data. Unlike traditional ML methods, which may rely on handcrafted features, deep learning can automatically discover representations from data, making it particularly powerful for high-dimensional and unstructured data like images, sound, and text. The next point is key concepts in deep learning. The first key concept is neural networks. Modeled loosely on the human brain, neural networks consist of interconnected nodes, neurons arranged in layers. Each neuron receives inputs, applies a weight and an activation function, and passes the result to the neurons in the next layer. Common types include feed-forward neural networks, convolutional neural networks, and recurrent neural networks. Layers. Input layer, the first layer that receives input data. Hidden layers, the layers between the input and output layers that learn representations. Output layer, the final layer which produces the prediction or classification. Convolutional neural networks, primarily used for image data. CNNs use convolutional layers to extract spatial features. They consist of layers like convolutional layers, pooling layers, and fully connected layers. Recurrent neural networks, designed for sequential data like time series or text. RNN have memory, allowing them to retain information from previous inputs in a sequence. Long short-term memory and gated recurrent unit (GRU) networks are special types of RNNs that can capture long-term dependencies. The next key concept in deep learning is activation functions. Functions applied to each neuron's output to introduce non-linearities, enabling the network to learn complex patterns. Common ones include ReLU, sigmoid, and tanh. Loss function measures the difference between predicted and actual outcomes, guiding the network's learning. Common loss functions are mean squared error for regression and cross entropy for classification. The next key concept of deep learning is optimization. Algorithms like SGD, ADAM, and RMSProp are used to adjust the weights to minimize the loss function. The next key concept of deep learning is backpropagation, the process of calculating the gradient of the loss function and propagating it backward to update the weights. The next key concept of deep learning is training and overfitting. Deep learning models require large data sets to train effectively. Overfitting can occur when the model learns noise in the training data, which techniques like dropout and regularization can help mitigate. The next key concept of deep learning is transfer learning, leveraging a pretend model on a new but related problem, reducing training time and data requirements. The next point is applications of deep learning. Computer vision, image classification, object detection, image generation. The second application of deep learning is natural language processing, NLP, machine translation, sentiment analysis, text generation. The third application of deep learning is speech recognition, transcribing spoken language, voice assistants. The fourth application of deep learning is generative models for image synthesis and other creative applications. The next point is why deep learning. Deep learning has become a go-to approach for many advanced artificial intelligence applications because of its ability to automatically learn and extract intricate patterns from large volumes of data with minimum manual intervention. Here are some of the main reasons deep learning is so valuable. The first main reason is powerful feature extraction. Unlike traditional machine learning algorithms which rely on hand-engineered features, deep learning models automatically learn features that represent data effectively. This ability to automatically extract complex hierarchical features has been transformative, especially for unstructured data like images, audio, and text. The second reason why deep learning is so valuable is high performance on complex tasks. Deep learning has demonstrated state-of-the-art performance in areas like computer vision, natural language processing, speech recognition, and robotics. It can learn directly from raw data, recognizing complex patterns that simpler models would miss. The next reason why deep learning is so valuable is scalability with data and computational power. Deep learning models improve as more data and computational power become available. As hardware, particularly GPUs and TPUs, has advanced, it becomes more feasible to train larger and deeper models on large data sets, leading to increasingly powerful models. The last reason why deep learning is so valuable is reduction of manual feature engineering. Traditional models often require domain experts to design features tailored to each application, which can be time consuming. Deep learning automates this process, reducing the need for extensive engineering. This is especially useful in fields like computer vision and NLP, where features are complex and task specific. The next point is why to use or when to use deep learning. While deep learning is powerful, it's not always the right solution. It tends to be best for application with large amounts of data, unstructured data types, or complex patterns that simpler models can capture. For smallest data sets or when interpretability is essential, traditional machine learning or simpler models might still be better options. How DL works. The next point is how DL works. First step is architecture of neural networks. Second step is forward propagation. When input data enters the network, it's processed from one layer to the next in a process called forward propagation. Each neuron receives a weighted sum of inputs from the previous layer, applies an activation function like ReLU, sigmoid or tanh, and passes its output to the next layer. This continues until the data reaches the output layer, where a final result such as classification label or a numerical prediction is produced. The next step is activation functions. Activation functions introduce non-linearities to the network, enabling it to model complex patterns and relationships. Common activation functions include ReLU, sigmoid, tanh. The next step is loss function. A loss function or cost function measures the difference between the model's predicted output and the actual target values. Common loss functions include mean squared error, often used for regression; cross entropy, commonly used for classification tasks, especially multi-class. The next step is backpropagation and gradient descent. Backpropagation is the process of adjusting weights to minimize the loss function. Using gradient descent, the model calculates gradients, partial derivatives of the loss function with respect to each weight. By moving in the direction of the negative gradient, weights are adjusted so that the loss decreases. This process repeats for many iterations over the dataset, gradually improving the model's accuracy. The next step is training the model. Training involves feeding data through the network, calculating the loss, backpropagating errors, and adjusting weights. Over time, the network learns patterns and relationships in the data. As training progresses, the model gets better at predicting outputs based on the pattern it has learned. The next step is regularization and dropout. To avoid overfitting when the model learns too much noise from the training data, techniques like regularization and dropout are applied. Regularization, example L2 or L1 regularization, penalizes large weights, encouraging the network to keep weights small. Dropout randomly drops nodes during training, prevent the networking from relying too heavily on specific paths and helping it generalize better to new data. The next step is evaluation and tuning. After training, the model is evaluated on a separate validation set, data it hasn't seen before, to assess how well it generalizes. Hyperparameters like learning rate, batch size, number of layers may be tuned to improve performance. Once satisfied, the model is tested on a final test set to verify its accuracy. And the last step is deployment and inference. After training and evaluation, the model can be deployed to make predictions, inference on new unseen data. Inference involves feeding data through the network and obtaining predictions similar to the forward propagation step during training. So I hope everyone must have been familiar with deep learning, or at least everyone must have gained 50% knowledge of deep learning. So that's all for today. Thank you for listening me patiently. Let's meet in the next video or during the next session.